September 11th. And it turns out it was a controversy. I'll stay away from that. And so I'm going to stay focused today. Except right now we're going to talk about, I had ChatGPT put together this table. This is wrong way incidents on I-90 in the Bozeman corridor in the last 10 years, right? So it's been happening a lot lately. I thought it was last year. I guess they're all moved. This is the college kids that were killed.
Yeah. What happened in Missoula yesterday?
Was there another wrong way driver in Missoula?
2 a.m. drunk.
And was there death? Did they hit somebody? No.
But
I mean, look at all of these.
Yeah, that's insane.
Right? April 22nd. There's in Manhattan. There's
So
one
how
woman
did you
killed.
just
That one
pee
was.
in the ignition. Yeah.
Isn't that crazy? So be careful on I-9. Literally, like I went to Seattle this year. I didn't even think about it. And then we came back to like Gallatin County. I was like, I'm driving in the right lane when you're driving into town. Because some of these are like in the middle of the day too, right? All DUI related. Not all of them are DUI related.
They were talking about it on the radio today. They said numbers are going down.
They are going down.
Yeah, because they're like adding warning signs.
Yeah, they have some flashing lights and stuff like that to try to prevent people from going out there. So be careful. Be careful. And don't do it's okay to break one law. That's another. Don't do that. They're breaking at least 2 laws. Yes, I get it. Right. But don't do that. Okay, that's it. Then there's this one. This is the time saved. This is time saved by the speed that you're going on a 15-mile trip. So this would be, and this is relative to if you're traveling 70. So if you're going to Bridger, I mean, just to show you that the time saved, like plateaus. It plateaus. That's what I'm trying to show here. Right? Is that there is no, right? And obviously there's a benefit from going really slow. Then you hit, but the difference between going like 50 miles an hour and 70 miles an hour, right? We're looking at, 5-minute difference, right? And then if you're going between 80 and 70, again, that's like a 2-minute difference. Right? So when you're driving down the canyon to Bridger, it's not worth speeding. It's not worth passing like 10 cars. You're looking at saving like 2 to 3 minutes. It's not worth it.
Someone driving 5 miles an hour under the speed limit is more likely to cause a crash than someone.
Yeah, fair enough. But at least the energy. Here's the energy associated with traveling faster, right? So the time saved is asymptotically approaching like a limit, whereas the energy is exponentially increasing as you're going, right? So the difference between driving 70 miles an hour and 100 miles an hour, there's a factor of 2 in terms of energy, right? And so it's more dangerous, right? Here's the same plot for going 100-mile trip. 100-mile trip, right? You are getting a little bit more, you get a little more benefit, but again, still, it's plateauing, right? So driving 100 versus 70, you're not gaining that. You're gaining a 30% difference in speed. Worth it other way.
How much time is that 30% for that one?
It's 25 minutes. In a 100-mile trip, it's 25 minutes. But you're driving 100 miles. Yeah, I know. But you're driving 100 miles an hour. It's dangerous. Right.
You know what I learned from that, though? Is that if the speed limit's 10, going 30 saves you a lot of time. If it's 60,
oh,
70.
God damn it. Come on, Luke. You're not allowed to talk anymore. Okay, back to this. You're right in that range. It does, yeah.
Where is the speed limit?
Yeah. School.
100 yards.
School zones.
Those don't last very far, and it's 50.
School zones. Fuck. Oh.
Parking lot.
Parking lot.
That long.
But again, the length of it's really short. So the amount of time savings.
30% is 20 seconds.
It's 20 seconds. That's right. Yep. Okay. Let's do it now. All right. Back to pre-stress. Pre-stress. Oh, by the way, I started looking at masonry yesterday. I started putting it together a little bit. It's like, I should probably get. I'm fucking terrified. I am so scared. I'm really scared. Oh man. Whew.
Have been the same notes for the last 20 years. Those notes are older than I am.
Yeah, they're really old notes. And then I did find what code governs it. I found that yesterday and started the process of getting it. Yeah, that's a good first start. What?
I thought Tim gave you.
Yeah, but his is from 2011. So what he had is pretty old. So.
What's the newest one?
What's that?
What's the newest
22.
22.
Yeah. So.
You went 11 years.
So anyway, so I'm getting there. I'm starting early because I knew what it was going to be like.
What happens when skiing starts though?
Well, it's in the afternoon. So I got
Oh, the classes after.
the class is the afternoon. Yeah.
That's sweet.
What? It's 3:00.
That's-
What's wrong with
Monday,
that?
Wednesday,
I know.
Monday,
Tuesdays
Wednesday,
are gonna be
Friday.
at 8.
Max is always at 8 or 9.
Yeah. Did you get to do homework in between?
I live 30 minutes away.
Mike, how about
Not my
we do what we did in
And Tim
computations?
teaches.
I'd be
Go
down.
an extra 15
Yeah, I'd be down.
Right? So it's gonna be
I'd be down for that.
3.
No, Friday.
Gavin is recommending
Oh, no.
double
He'll
it,
like it.
doing a little bit more on Monday and Wednesday and
Oh,
skipping
yeah.
Friday.
Yep.
Yeah.
Yeah,
Let's
you
do
can
it.
show
Let's
us.
By the
do it
way,
all- Let's do it all on Monday.
Just do 3 hours on Monday.
But then you're done at 9 on Wednesday and Friday. You're done at 10.
Okay, I'm ready now.
Can we go
Yeah.
from 3 to 6?
I think I
One day a week.
Monday. We're not gonna do it. We're not gonna do it for 3 hours.
3 to 9, and we just do 2 weeks in 1 day.
That's a great deal. That is beautiful. I think Tim worked it out, and I think it's was it like
Let's do
just like
44
40 hours over the whole semester or something like that. So let's do the whole semester. We'll just do it 8 to 5 for the whole week. 2 include weekends. Yeah, that'd be a good idea. Or just do 2 weekends.
Start Monday, exam Wednesday,
Okay.
exam Friday. Done.
Okay. All right. I'm saying on topic. Okay. So here's the general equation, right? VVN has to be greater than or equal to VU. Okay. What is VN? Right. This is the same equations. It's under the same section in ACI. Right. It has it's the same general equation for this 20. I think it's chapter 25. We'll look at it in a few minutes. Right. So everything's the same. This is what I wrote. This is the last thing I wrote. It took me 15 minutes to write this last time, okay? So VN is going to be VC plus VS, okay? VS is the same as what we have done before, right? This is the same. This is capacity from the steel. From steel. From transverse steel, I should say. Right, if you have stirrups in there. Same as regular reinforced concrete, right? Same equations as a AVFY D over S, I think is what that is, but we'll look at that in the code in a little bit. Okay, so it's the same. What's different, obviously, is this VC. Typing back to normal. Right, so this is the concrete capacity. The C standing for concrete. Okay, this is more complicated for pre-stressing than it is. It's actually very complicated. Like I said, this is going to be quite the exercise of going through the empirical stuff in ACI. Right, axial load or axial compression load on beam increases shear capacity. And we'll explain how it does that in a minute. Vertical component of pre-stressing can help. I'll give you a little figure of that in a second. Right, there's multiple failure mechanisms. That we have to be worried about. And the other thing that complicates things is EP changes along length. But it's delayed here. Right, so these are some, and we're going to dive into these VC a bunch here in a second. Okay, so it's more complicated for an axial compression load on the beams, right? Because everything's pre-stressed, so they're axially loaded, And then the vertical component of pre-stressing is this. If you have a harped, right, or a draped section, right, there's a vertical component to this. Right? We kind of ignore that. We ignore that vertical component. Right? We just pretend, if you remember that, in our pre-stressing, we just pretend that these stresses are acting horizontal, but there is actually a vertical component to that. And so some of our design equations will have that vertical component in it. Okay? To account for that, the help that that gives. Doesn't help a lot, but it's something. Okay. We're gonna do, this is what I like. I like teaching mechanics stuff, right? So we're gonna do some mechanics here and talk. Oh, that's a Morse circle. That's a Morse circle, Garvin. Yeah. We don't have to do. We don't have to actually use it. We're just using it to demonstrate something. Okay. You don't have to draw more circles. I mean, we're gonna. I drew the Morse circles for you on this. Okay. So this is this is a common thing you should get used to anyway. When you're talking about, right? Usually talk about the pre-stressing on the end here. We talk about a little block, little stress block over here on the side, right? We have a positive shear applied to this thing. Positive shear looks like that on that cross section, okay? And so what does that look like when we look at our stress block? We're gonna draw our stress block just for regular reinforced concrete right here. There's my stress block. And then I have stress is acting on here. I have that positive shear here. On the other side, it'll be this direction. It'll pinch towards the corners. This is what this is what the state of that stress block looks like, right? So I've just taken this and I've blown it up. Right? So that's a pure shear. And on the end here, you draw it on the left-hand side here because the shear demand the moment demand over there is zero, right? There's very small, right? So there'd be no normal forces on this. It's just a state of pure shear on the very end of this thing. So it would look like this, okay? And so then what you do, right, is you put this thing in it, you look at its principal stresses. You remember doing this? Okay? You do this. You probably did this in concrete. It's solids, yeah, right? So you flip this guy on its side. Let me see if I'm gonna copy it. Uh-oh. They updated this system here and it's driving me nuts. Oh, I'm so mad at this update. How do I rotate this bitch? Huh? I want to rotate.
Well, if you cut it and paste it, it should give you option. They updated GoodNotes like 30 seconds ago.
They did updated it this morning. I could type now, but now I can't rotate shit.
Redraw it.
I don't want to redraw it, Neil. I want to copy it and rotate it. God damn it. I'm going to do it in Neil's head. I'm going to freaking draw it. I'm so sorry. I'm not. See, Neil? Does it look good? God damn it. Let's try one more.
Rotate the freshly drawn one.
Man, imagine not being able to rotate.
I do. Oh, those sons of bitches. Why won't it let me do that anymore? God damn it. I guess we just rebuild. Okay, all right, fine. Let's draw it. Just It's like making it into a diamond. Close enough.
Is it a rotated square?
I rotated it. Right? I rotated it 90. Oh!
No, I'm just saying, is it not a rotated square?
It is, but I wanted to just copy it over.
What's the angle?
I wanted it to be 90. Okay, fine. You get it. All right. I'm obviously getting a little around here. Wait, sorry. Nika, I'm trying to stay on topic today.
Is this not the topic?
You know, you're making fun of Mike's geometry skills and my drawing skills, right? So it'll pinch like this is what it'll do, right? This is what those principal stresses will look like. Right? Do you rotate this block 45 degrees, right? That's what the principal stresses are. If we were going to go to what you would actually do if you were to look at this in Moore's circle, and Moore's circle is really good for picturing what's happening here, right? So if I drew this state on Moore's circle, right? I have a positive negative shear, but I have zero normal stresses on these faces, right? So there's no normal stresses on those faces. So what I would do is I draw the shear here and the shear here, the positive and negative shear there, right? That's what you do. And then you draw a circle around, right? And that's where you get these principal stresses, right? You're gonna get one in compression, that's this side is in compression, and the other one is gonna be in tension, right? So here's the tension side going like this, right? And here's the compressions coming in like that, right? And then a rotation of 90 degrees on Moore's circle is the same as 45 degrees in the real world, if you remember that, right? So this is, I got to go from this state to this state, I'm rotating 90 degrees, which means it's 45 over here. And then I guess the whole point of this is to show that what I'd get is I would get a crack like this, right? This tension stress, this is how concrete fails due to shear. It's due to these tension stresses. Those tension stresses get to a certain point, and then it causes the concrete to crack, right? And it gives way. What that would look like, that would be this point right here. Okay? And this would be, according to ACI, this would be the rupture strength. FR is equal to 7.5 square root F prime C. Right? So this would crack when my tension stress over there hits 7.5 square root F prime C. Okay? If I'm going to add pre-stressing into it, let me do that. Now I got to copy these guys. Right, so we're in a case of, see, I'm mad at I want to rotate it again. Erase this one. This would be a case, if I have pre-stressing, I would have a big normal stresses doing this. I used to just make it straight across, and now it puts it at an angle. Mad at it. Right. We've added pre-stressing to it. And that pre-stressing on that beam up there would be a normal stress acting this way, not this direction. We're not going to have any this way. Right? You won't have it that way because there isn't pre-stressing in that direction. There's only pre-stressing in this direction, right? So on one of the faces. So then on Moore's circle over here, what that would look like, right, is I would have one face would have 0, right? So that would be zero normal stress, right? There's my normal stresses. 0 normal stresses and a shear. That'd be that point right there, okay? On the other face, I would have a normal stress and its compression, right? So it'd be this direction on that diagram because that's a negative value, and then it would be the positive same stress. So it'd be this point right here, right? And then you just draw a circle around that, okay? And the whole point of doing this is to show you what happened to the tensile stress when I did that. They have the same shear stress, but then what happened to the tensile stress? It moved to the right, right? So now, while this one broke, right? This right here broke at, with a shear stress of this amount, right? It broke because it ruptured like that. This one won't break because at the same shear stress, right, it no longer reaches that 7.5 square root F prime C because that compression holds things together, right? That's my graphical appeal to you. Principal stress is what's happening. And the other way to think about it is, right, the concrete fails due to tension. We add some compression in there, and then it doesn't fail at the same load. Right? I mean, you could say it the same way, but as an academic, I got to show you Moore's circle. Okay, you okay with that? It's kind of fun, right? Moore's circle. When was the last time you saw that? Geotech? Oh, in
Monday.
you did it on Monday. All right, never mind. So there you go, right? So it adds that and it shifts it over to the side, right? Which and then the angle would change too, right? The angle changes. It's not at 45. It'll be steeper. Oh, God damn it! That's what I want to rotate. I'm gonna try one more time to rotate it. I feel like that should be a common. See, there used to be. You could see that. Yeah, there used to be like a thing that was pulled down, and then I could grab that and I could drag it around. I don't. What happened to
Something
that?
like that.
Ooh, what if you select it, like draw the circle around it, and then press and hold?
Okay.
Shouldn't it give you a menu?
Yeah, you can't see it. I got paste and match smile, zoom. Oh wait, I got selected first. Hold it, and then I could say convert, screenshot, color, resize, edit, good.
Maybe it's edit.
Edit handwriting.
What? It used to be resized.
Yes, there's resize.
It's me too.
Just don't update stuff, man.
You won't let me do that. Don't update it. Don't update it.
Oh,
Okay, I'll just draw it again now. I'm so excited about the new update. Now I hate it.
Why don't they still fix this up?
What do you? Oh my God!
I think it's an apple. That's the difference.
whoa.
Fucking thing. It's not as steep. Hey, why can't I draw? I'm just gonna back to the old days. I'm gonna freehand it. Oh God. There we go. Fair enough. Right? The same thing, right? But it's just a little bit steeper. And so they won't be at 45-degree angles, right? It'll be a steeper crack that forms. Okay. All right, and so the big part here, right, is pre-stressing, shifts, circle, left, and makes bigger. That's the key takeaway from all that, right? The pre-stressing, increases the shear capacity, right? So we do Morse circle advanced mechanics, huh? So just in case you didn't have enough Morse circles, I made some more. I made some more Morse circles. Okay. This is MATLAB, yeah. This was obviously from several years ago, and I made a function called Morse circle, and then you just gave it things, and then it would plot the thing, and then I had a little extra time in my hands. Just like yesterday when I made those plots about the velocities, I made those in MATLAB too.
You get scared by masonry and
And I was like, oh God, I'm going back to this stuff. So what we got here, this is just more like with actual real numbers and stuff, right? So this would be just the case right here. That's my blue one, right? That's my base case, which is just a shear of 20 and a sigma x of 0. So there's no compression on that one, right? And that one would fail. So according to this, that one would, this would hit the, 7.5 square root of f prime c. So if that's where that one would break, okay? So then I just took the same stress state, the same stress state of 20, a shear stress of 20, and then I just added a compression stress of negative 20, so in compression. So that's what this red one is. And again, just to show you that it shifted it to the left, and so that one would no longer fail, right? Because it's not hitting that 7.5 square root of F prime C, right? And I did another one, this one right here, that would be the case there. That would be 20 and then 30 for the pre-compression. So we're adding even more pre-compression to it. And so that one's even less likely to fail, right? If I wanted it to fail at a shear stress of, if I wanted to fail with a normal stress of 20, if I wanted it to fail the normal stress of 20, that is this guy right here, this pink one. And so in order for it to get that one to fail, it'd have to get bigger, and because it's shifting to the left, I'd have to put more shear stress on it to hit that 7.5 square root F prime C. So it'd be 28.3. I would have to increase. I mean, there's your difference, right? At 20 PSI in compression, at 20 PSI in compression, I would have to apply a shear stress of 28.3 on it, versus if I didn't have any stress on it, it would fail at that. Oh wait, hold on. No, this one. It'd be this one. It'd be this red one versus the purple one, right? So if I had 20 on it, I'd have to get it up to 28.3 in order to get it to fail. And then the last one, this is just kind of an exercise, just to look at it, just to prove to you this happens. This would be the case if I have shear stress in both directions, pre-stressing in both directions. That last one is going like this, a compression this way and a compression this way. That's the black one. If I had that case, then this sucker, you would have to get out to a shear stress of 40 in order to fail it. They actually do this. This is real. They do this. And this is in like big box girders. You ever seen big box girders? Sometimes big boxes that are girders, right? And they'll actually put pre-stressing longitudinally that way and transversely on it to kind of hold it all together to keep it from cracking. And so in those cases, their shear capacity goes way up. Anyways, that's a more circle business, which I like. Okay. So some more theory to get into, right? Because all this stuff is behind what we're gonna get to. You don't see Mohr circle, you don't see anything like that in the actual design equations. Actually, by the time you're done with the design equations, you're gonna wish that you did Mohr circle. That is a 100% true statement. It is 100% true, Garvin. Okay, so where are we gonna see problems, right? We talked before, like, in these beams up here, right? If you have a dapped beam, right, you can run into some problems there. And then usually it's going to be in the web because of this. But then, like, where at along the length of the member are we going to run into problems? Right? Obviously, dapped ends would be right where that dapped ends is. Okay, so this is all in Stanton's notes. These are associated with, I've just taken the stuff out of Stanton's notes. So what we said before, that's what our shear stress distribution is going to look like in a typical I-beam, right? Near the end of the member, when there is no external moment on there, we're going to have a lot of pre-compression, right? Because near the end of the member, the moment zero, so you have, this is the case where the thing's popping up, right? Where you have a bunch of pre-compression at the bottom and a little bit less at the top because it's kind of bending up. But I have most of my section is in compression. If I have a lot of my section in compression, then this is happening, right? I'm getting the benefit of the compression, over the entire height of my member, right? Over the entire height, I have compression, so my shear capacity has gone up, right? Great. The problem with that is the demand is really high over here too, right? So my capacity is high and my demand is high. So over on the left-hand side, right? Capacity, I say, maybe it's better to say there's a demand high, but capacity is high. Most of section is in compression because no moment or low moment, you get it. Okay. Near the middle, right, you're going to have a lot of external moment pushing this thing down, right? You have the external moment pushing it down, and you're going to have some tension, right? You're going to have some tension down at the bottom up until what we're allowed to have, and then you're going to have, really low compression and then up to some really high compression. So your capacity near the middle is going to be down, right? Because near the middle, right, again, we're going to have part of our cross-section is going to be in tension. So the opposite will happen. If you add tension to these more circles, it's going to cause it to fail even faster in tension. Compression helped you. Yeah, tension is going to make it even fail even faster. So near the middle, there's going to be parts of our cross-section that are in tension. But the benefit, our capacity is down, but also the demand is down, right? The shear demand, here's the shear diagram right here. The shear demand near the middle is really low. So now here we say shear capacity low, but so is demand. Right? So that may not be the trouble area. Where the trouble area actually is, and you'll see this in your homework, is in here. Not like that. Oh, I'm so mad that you can't rotate these things. Like, I bet it won't let me even do an oblong one anymore. See? There's got to be something. Okay. Anyways, that's fine. Right? It's going to be somewhere in here. Like I said, in our homework, you're going to see that. That is where it has a problem. Right? Somewhere between the middle and the ends. Like I said, in your homework, you'll see that if you do your homework right. I'll do the same thing that I did with this one, with this upcoming homework, as I did with that homework 2, where I'll give you the solution, and so you can look, you could make sure your diagrams are matching my diagrams, because there's so many places you can go wrong. The other thing I'll mention now, if I forget to say later, I'm going to sign it. The other one's due on Friday, right? So I'm going to sign one on Friday, and then I want you to really try it, because one day next week, next Wednesday, I'm going to go through it with you, because there's so many. You guys are all going to have the same questions, but you have to try it first. I'll bring this up on Friday again. You have to try it first. It will not be worth anything to you if you haven't tried it. You'll see. I'll give you all sorts of... I'm going to go no notes here with you. Yep, okay. That makes sense to everybody why it's happening in there, right? High demand, but high capacity, or other way around, and then shear capacity is low, but then the demand is low. So it's going to be somewhere in between, right? So where at on the beam are we going to run into problems, right? On the beam itself, we kind of alluded to this, right? You got lower shear demand in the in the flange, right? Because there's not much there, because the VQ over IT, the T is really big, and so there's really low shear stress right there, right? Where you're going to run into a problem, right, anywhere, so it's going to be in the web somewhere, right, because the demand is higher in the web. And then it's going to start down here. And the reason it's going to start, you're going to have issues down here is because we have tension down there, right? Remember, tension makes it worse. So you're going to have tension down here near the bottom, and then you have compression at the top. So at the top, my capacity is actually pretty high, but at the bottom, my capacity is low. It's high because I have a bunch of compression up there, but at the bottom, I have tension, so it's low. And so what it'll do is it'll start near the bottom, right? It's actually going to be right here. We have issues here. Shear demand high, and beam may be in tension longitudinally. Okay. So types of failure mechanisms that we'll see. I don't know why I didn't give you pre-drawn beams, but I'll do it. I'll draw a beam now. Oh my God. That was a rectangle. God damn it. I need that tool. So flexure shear failure. Why? Oh my God. The flexure shear failure, it's going to do this. It starts out as a flexure crack, goes up like that, and then it turns into a shear crack. Right. Starts with flexure. Ooh. Oh my God. Flexure crack, which increases shear demand on section above, which leads to crack in shear. Okay, so it starts out flexure, the demand gets bigger, and then it shoots across like that. Okay, this is in the web that this would be happening, right? And actually, it'll initiate in the flange and work its way up. In ACI, this is VCI. VCI in ACI. Okay. If you're reading through Stanton's notes, or when you get to that, when you're reading through on this section, he has a big, long section, and he derives the VCI equation in ACI. Don't do that. You get to his like derivation and stuff, just ignore it. Okay, we're just going to use it. Don't worry about the derivation of it. Because, like I said, it's pretty nuts. Okay, but that VCI is for the flexure shear, right? And if we have web shear, it just fails directly in the web. And if this is an I-beam, you have the flange down here, the flange up here. And you just start getting cracks where you don't actually see any. They don't initiate as flexure cracks. The web just fails in shear. Shear capacity of web is reached. And shear cracks form. This is VCW. VCW in ACI. Right, and there's going to be a calculation that we do as we go through where we don't know which one of these things is going to fail. I don't know, is it going to hit my flexure shear capacity first, or is it going to hit my VCW first, right? And so you have to end up calculating both of those, and then you grab the lower, the weakest link, right? The thing that gets complicated, just to set the stage for this, is that it can change along the length of the beam, right? In one location, it might be VCI that's controlling, and in another location might be VCW that's controlling. And so you end up with a plot of both of them going across, and then you grab the minimum of the two as you go across, and that gives you your limit, okay? Just to give you a little foreshadowing where we're headed. I have the solution somewhere. Nope, I don't have it in there. I have it in here. Does it make you dizzy if you look at that? And we're going to calculate that. There's two different methods that we're going to use. Your homework this is the solution to your homework. Like in some cases, right, there's a certain limit that's controlling here. Then there's another limit that's controlling here, and then there's another limit that's controlling here, and then another limit that's controlling there. Great, right? So and then if you really looked at all of these, there'd be one that's going like this, one that's going like this, another one's going like this, and there's like built into my code, I'm grabbing minimums as we go along, and then that's formulating that envelope that we have, right? And then my demand is this guy going across, right? And so, like I said, right, where you're going to run into problems is somewhere in between, right? So this is my demand. This is where my capacity dips below my demand is someplace in the middle. It's fine on the ends, right? It's fine in the, this is just half the beam, so it's fine in the middle, but it's in between that it's violating that. But we'll get there. Okay, so let's look to see what ACI has to say about it. Wait till you get a load of this. Starts out pretty innocent, right? So let's look at the ACI equation. So it's 22.5 is shear capacity in concrete. So 22.5, we get right here. It starts out for both. This is just general. This works for both regular reinforced concrete and pre-stressing. Again, pre-stressing is built in throughout, right? So my VN is just VC plus VS, right? And what we use for VC, there's still this limit applies here as well. Right? This is just a limit on cross-section size. This is built into regular reinforced concrete limits that you've done before. So there's that limit right here. And the only way you can change this is changing your cross-section size, right? And it says for pre-stressed members, VC, VCI, and VCW shall be calculated in accordance with these two sections, 22.5.8, 22.5.9. Okay, so there's this section that discusses this. It's going to make it an oval, I guarantee it. So mad. Oh, and it tries to turn it into text. Okay. For calculation of VC, VCI, VCW, lambda should be in accordance with this. Lambda is just is a lightweight concrete thing. We're going to stay away from that, but there will be a lambda floating around. That's associated with the lightweight concrete. Okay. Then we come down. Geometric assumptions. This is a limit that's going to be built into all of our code. I don't know why it keeps doing that. It crashed on me. Okay, so for calculations of VC and VS in pre-stressed members, D shall be taken as the distance from the extreme compression fiber to the centroid of the pre-stressing and any non-pre-stressed longitudinal reinforcement, but need not be taken less than 0.88. Okay, so that's something that you'll have to build into your calculation, is that it's the distance, right? Because what's happening is D is changing along the length, right? So if it's a harp section, right? Let's look at it like this, right? It's a harp section, it's going, oh gosh. Oh my God. Right, my EP is changing, so my D is changing as we go along. The D is the distance down to the neutral axis. It's from the extreme compression fiber. I guess I should put a beam around that. Oh my God. Right, it's the distance. This is the distance D right here, right? From extreme compression fiber down to where the steel is. And it's going to change as we go along the length of it, right? Because our steel location is changing as we're going across. Our pre-stressing is, right? We're making it deeper near the middle and more near the centroid along the side. But when you're calculating this D, this is what it's saying, when you're calculating that D, eventually that D could go to 0, right? Because, right, if this was right at the centroid, if that was right at the centroid, or not 0, but it would become really small, right? Because it's going up to the thing. It need not be less than 0.8 H. It's saying that, like, even though your D is less than that, you can use up to 0.8 times H. H is the total height on this. You can use up to 0.8 of that. Right? That'd be your H. And so it's saying you could do that. So and it would be, could you use smaller? Yes, you could use smaller values. But if you do that, then you're being overly conservative, because the code allows you to use 0.8 H. You don't have to go smaller than that. Okay? So that's a limit that's floating around. Okay? The other thing they put in there, I don't think this is going to affect us at all, but there is this right here. Oh my God. I wonder why it does that. So mad. As an engineer, I want to box it. I don't want to oval it. I don't oval my answers. You oval your answers? No. at right angles. There's a limit on the squared F prime C. One-way shear shall not exceed 100 psi. So they just haven't, they don't have any, so this would be for, so that would be an F prime C of 10,000, all right? 10,000 psi or 10 ksi. You basically, if you have a 10 ksi concrete, you take the square root of that, that'll be over 100. It says you can't go over 100. Just there's no research showing these high strength concretes on the shear capacity, so they put a limit on it, saying that you can't in those equations. You can use over 10 ksi concrete, but in these equations you can't use more than 100 psi for the square root of that 10 ksi. Okay, that's another thing. Just keep that in mind as we go through. All right, let's see what else we have to mention down here. This is what you do for regular concrete, just to show it to you here. Right, there's your 2 squared F prime C BWD, right? And then there's a more detailed method, right? This will show up in one of our equations. That's why I wanted to box it here. But that's what you would usually do. So you can see that that's where it defines VC. You keep going down. Is all non-pre-stressing, and then here we go. Here's for pre-stressing. Pre-stress members. Right. There's 2 different methods you can use for calculating this. The section applies to all calculation of VC for post-tension pre-tension members in regions where the effective force and the pre-stressing reinforcement is fully transferred to the concrete. For regions, pre-stress members where it's not fully transferred, then you do these things. So then this is saying we're going to do this method. So according to that thing, you're going to do 2 different methods. You're going to use this guy. Oh, I want this thing. I want that. Use this guy. That's one of the methods. That's 22.5.8.2, right? And it says, here's your equation. So this is the simplified approach, right? This is the approximate method. This is the easier one to do, okay? Then the VC is going to be the least of A, B, and C. So you're going to calculate every one of these, A, B, and C. It's going to be different in different locations along the length of the beam, right? You're going to calculate this value. It's very straightforward. You just put in the values that you have. Be careful of all your units. Be careful. There's some assumptions over here. You should take advantage of this if you can, right? They have some limit, or they have a calculation for what this value is. VU dP over MU, right? That can be substituted in right there. Okay, but then you'll calculate this, you'll calculate this, and you'll calculate this along the whole length of the beam, and then you'll take the minimum of each one of those things, right? So on this solution here, like I said, you'll see one of those. This is 22.5.8. I think it's this one right here. That's one of those limits. That's like A, then this one's like B, and this one's like C, something like that. I don't know exactly what it is, but then it's somewhere along. I don't know which order they are in, but that's the 3 that are there. So which one of those controls is going to be dependent on where you're at in your beam, right? So you have to calculate all those things along the length, right? And then what we'll go into next time we meet is the next section. That's the simplified method, and then we'll do the one where you calculate VCI and VCW. So VCI, here's our equation for VCI. It's either this one or this one. It's a function of M cracking, which is that equation right there. Huge discussion of stuff over here. Then we get down, and here's finally VCW. VCW will be this, but it has some other limits associated with it right there. And then there's all these other terms that are floating around that it uses. And what gets really complicated is ACI uses variables like FPE, lowercase FPE, like we use lowercase FPE, but they're different FPEs. My FPE is different than their FPE, right? There also is different Ys floating around that we have to be careful of what we're using, because their nomenclature is different than our nomenclature. And so you just gotta be really careful with all that stuff. But again, that's what I want to go over with you. Once you've tried doing a little bit, then I will come in and I'll say, here, be careful of these spots. Okay, much more productive.